Salam, do you hear me? If you hear me, please write down your preference of language. Do you prefer English? Do you prefer Arabic? No, Arabic not. I cannot speak in Arabic. Do you prefer Persian, Arab, English, or a mix of them? Allah, which one do you prefer? I will ask by name. Allah, your microphone is online. You can write here at chat box. You all connected with your mobile phones. It's not the perfect way of joining the class. You must use laptops or personal computers. Please use your laptops and PCs for joining the class. Mobile phone is much limited to see the class and interact with. Do you hear me? My microphone is open. Let's Then if you hear me, which one do you prefer? Nejud Abdus-Sattar, do you prefer English, Arabic, Persian, or Arabic? Not, I cannot speak in Arabic, but I can speak in Persian or English, or a mix of them. Which one do you prefer? Which one do you like to hear me? Let's start here with the polling. Add the new poll. Which language do you prefer for the class? English, Persian, plus English, this is words, no. Muayyad Khalid Muhammad. Dear my students, please contribute in the polling and select your preference. Which language do you prefer? Someone prefers English. Who? Okay, then we go on with English and hope that you benefit from the class. This is my first lecture ever in English language, and you may find it somewhat hard to understand, hard to follow, but you may try to watch the recorded lecture over and over such that you can get an understanding of the presented topics. Okay, this course is entitled Advanced Topics in AI, Advanced Concepts in AI. I plan to review the basic topics in machine learning in the course, and then we'll jump into the deep learning subjects as the modern development and computational contribution in neural network area. We have several online lectures, several offline lectures, and all of the course-related material are uploaded in this courseware. The address of courseware is CW1. Let's write here the courseware address: cw1.basu.ac.ir. You all have signed in the course page. I see that you have signed in, you have viewed some of the video lectures, some you have viewed some of the text uploaded there. Then you know what is the course, what materials, what contents it could have, it must have, and we are here at the first online lecture. To give you more stability on internet connection, I will pause my video. Okay, you may have a better experience with the connection. Video is now paused and won't use your bandwidth. I once again assert that you must use laptops and personal computers to connect to the course. Mobile phones, cell phones is not a good idea to use here because the content is presented in a wider screen, and I write with this regular font on the screen and use this somewhat regular font in slide presentations. It may be too small for cell phone screens. Please, next session, inshallah, you may use your laptops and PCs. Furthermore, I know that cell phones, many of the cell phone brands have difficulties with playing Adobe Connect online lectures. It is a known problem. Most notably, my audio, my voice may be garbled in your side. You may hear my voice in a garbled form. It may be related to your internet connection or may be related to device capabilities. Then please use the most efficient devices such as laptops, advanced tablets, or the best one, the personal desktop PC. You can record the lecture in your side. I'm also recording the lecture and will present. We will provide the link for you. The link will be uploaded in the courseware. During the lecture, you can use raise hand option in the screen and ask your questions. You can write here your questions in the chat box. I will answer in the middle of lecture questions. Your questions I will express, I'll describe, and I will try to clarify any points. So, In the first lecture, we will give an overview on the machine learning in its all and try to relate it to the topic of the course, that is the deep learning. Machine learning is somewhat a new branch of science, but it's as old as any topics in AI. The discipline, the machine learning discipline, tries to train computers to do tasks that normally human can do. Normally human does as an intelligent species, and we try to build computers, try to train computers that do the task like human. This may be some tasks that are human are very good at, such as recognizing faces, or some tasks that a normal human do very accurately, but it requires more time or more resource or more human power to do in a limited amount of time. For instance, indexing lots of papers and books in the libraries that a human or expert could do very accurately, but it requires lots of time to index ever growing amounts of books and papers and documents. So that the machine learning is a branch of AI that tries to train, if I want to give a single sentence definition of the machine learning, it is the art to train computers to program themselves. That is, as you know from the elementary courses of computer science, you program the computer, you write the algorithms. Given a problem, you write the algorithms, then program the algorithm into computer, give the algorithm some input, and get the output of the running programs. Here we want to program the computers, the machines. We want to train the computers to program themselves. That is, a computer programs itself to do some tasks, some intelligent tasks, some tasks that a human being does very well, and we want the machine do so. Normally, for this type of task that a human expert or a normal or generic human being does very well, we can have many input, output related data that defines a task, defines a process. That is, we want a computer program that, given a set of input and output, learns to predict the output for unseen or so-called new data. All we have in hand, all we know about the problem, the process, all we know a process we like. For instance, suppose that we want to train the computer to do face recognition, to recognize human faces. That is, to say identity, the name of the image belonging to face image belonging to. That is, given a face image of someone, says he is Ali, and another one says she is Sarah. This task, this process, is called face recognition. What is our task in machine learning to do this automatically? We should write an algorithm that, given a set of face images with their names, we give the machine a set of face images with their names. This is images, and these are names. These are images and these are names. And we want to train the machine to predict the name or identity of a new images. For instance, if we give an image of, this is Ali, if a new image of Ali, machine should know that he is Ali and identify he as the person who this image belongs to. This is the whole circulation of the machine learning process that we should do. How a normal human being understands that this image is a picture of Ali. He sees the picture, does some process, and refers to his memory and finds that this picture is a picture of Ali's face. How does he do this very complicated task? We do not, the nice thing is that we do not know for sure. We don't know for sure how a human being does this task very well. But we know that a human being is very well at this task. He could easily identify, recognize a human face inside of 100 of people. For example, in a ceremony, in a street, in a seminar, or any crowded place, you can identify your friend very well without even trying to think, without even trying to use any special devices. To do this with computers, we don't know the actual process the human follows. We don't know the actual process that this man follows, but we try. The key idea is this: we try to find a mathematical function, an algebraic function, if a math function if that given an image maps it to the identity. That is, y equals to f of x. We want to try to find f such that y equals to f of x. X here is the input image, and y is the answer. Several names this y has: the answer, label, output, and so forth. Many names, but the same meaning. Many names, the same meaning. The identity of the given image. For example, f may be a function that uses a lookup table for intensity of image regions. That is, suppose that this is a face image. This is a face image. Let's do some drawing. This is his mouth, his nose, and the image, the face image, is 64 pixels by 64, and we divide the image into 4 by 4 blocks. That is 64 by 64 pixels is divided to 4 by 4 blocks. For simplicity, please suppose that the image is a grayscale image, and values of the pixels, the pixel values are in the range 0 to 1. That is, here may be 0.7, the black people may be 0.1, and so forth. The average intensity of this block, I call it the average. We take the average intensity of the blocks. I call it here I0, the first block, I1, I2, I4. And finally, if you count on, you will find here I15. I of k is the average intensity of the block I. Average intensity, gray value of ith block. So what to do with these averages? I can assume that F is a lookup table like this. A lookup table is something like your phone book that you write names and numbers therein. You have a table like this. And here you have a corresponding names table. We take it block intensities. And here we write names. Let's divide the block one more time. That is, this is no W. We don't have any W's here. It is I0, I1 till I15. For instance, we recorded here that given the training images, given the labeled images, we record that if the intensity of this block I0 is 0.6, the next block is 0.5, the next one is 0.7, and then this picture, the corresponding name is Ali. Then this picture is Ali's picture. This is a lookup table with all training images. How we would use this program? Given an unknown image, I tried to express a very simple example. Given an unknown image, we are asked to know who is this. We do the same partitioning for this image. We do the same partitioning. Extract the or compute the intensities. I call these intensities something like, for example, x0 corresponding to the mean intensity of this block, x1 and x15. Then try to look up, to search for, to find this set of 16 values in the table of features. If I found the values, then I can be happy with the name. If there's no such values, there's no such set of values, then I can claim that the picture is unknown. I don't know who is in the picture, whose face is this. The simplest, the most simple machine learning program that uses a lookup table to record face images and tries to look up the person name by doing the same process on the given unknown image. Why we should expect that this algorithm should work? Why we do expect? The philosophical question is, why we do expect that this approach, this method of designing an intelligent program should work? This is one of the most basic philosophical questions on the machine learning. Why we do expect that this approach should work? I would like to should work. I would like to talk on this question from two different viewpoints. One is the hidden and the latent phenomenon. To answer these questions, I should express some basic information we all have, we all know, but rarely we use in our decisions explicitly. We use this information very implicitly. The first one is the latent versus visible world. What is this? The first observation, this first expression, talks about a box, a black box, that inside the box, maybe some process, maybe some machinery or people inside the box. We don't know what is there, but we see that every second, each second, a written piece of paper is drawn out. There is a written piece of paper is drawn out, and it has labels 1, 2, 3, 4, 5 or 6 on it. What do you think about this process? What do you think? How could you say that is there a single man rolling a dice and writing the number and throwing it out. How could prove that there's a single man that this does dice roll and throws a number out, or two people doing the same thing, or a machine, a cutter machine, actually a cutter machine with a roll of paper that has labels 1 to 6 on it. The cutter machine rotates the roll of the paper and cuts the numbers. That is, the box is something like, I hope to formulate the cutter. The cutter here is the cutter, and the paper is fed to the cutter cuts the numbers, and the numbers are thrown out. No dice, no people, a static process that produces the numbers, the numbered pieces of papers. Question: could you distinguish, could you identify which one of these three processes actually governs the box, actually does the process inside the box? Please answer me. Could you identify precisely what is inside the box? Here I am waiting for your answer. You just say yes or no. My dear students, I am waiting for your answers. Could you identify which one of these three processes is actually there and produces the written pieces of the papers? Muayyad, what do you think? Which one is there? Do you know? You could answer I don't know. You could answer the first, and you should justify your answer. Nejud, do you know? You all have microphones. Allah, do you know who is there? Okay. Please write here in the chat box what is inside the box that produces pieces of papers with numbers on it. Please contribute. Please answer the question. Please contribute in the lecture. Please answer my question. Okay, you don't like to answer, or you may not have access to your phone. Are you here at class? Are you there? Okay. Are you there? Please answer my question. Do you know what is actually inside the box? Okay, while you're trying to answer the question, there's no such thing as the correct or incorrect answer, or right or wrong answer. Actually, there may be a single man, there may be two people, two men, a cutter, or many other performing many other systems performing the same task. This is out of your sight. You don't see inside of the box. You don't have any clue about it. You see just the outcome of the box. And the sequence of numbers is 1, 2, 3, 4, 5, 6 for any of these systems, for any of these scenarios. Actually, you cannot say by sure that what is inside there. This is the notion of latent versus visible world, or latent versus visible phenomenon. That is, the process governing the whole system, the process governing the box, is out of sight of us. The process is invisible to us. What should we do? We could guess, just we could guess. We cannot say for sure what is in there. We just guess some types of activities. We could guess there's some processing machine, there's a couple of people, there's a roll of paper, and so forth. This is the notion of latent world. Where is the latent world? The actual process that governs or directs the system. And observable or visible world. What is this? This is the output or variables or effects we see. We could not say what is the real scenario, the real process. We see some observable. What we do with this latent and observable worlds, we take the observations, the visible outcome, we take our knowledge from mainly math and statistics. Please note, observations from the process itself, our knowledge from math and statistics, and build a system that behaves much like to the original one. We take the observations, we take the knowledge, our own knowledge from math and statistics, and build a system that behaves much similar, much like to the original one. Our system for face recognition uses average intensities in the blocks. Do the human use the same thing for recognizing faces? We don't know. They may use or may not. But we know from math that a numeric function that maps these averages to labels such as lookup table, a linear function, or any polynomial may help to identify the faces. How could we assured? How could we be assured? We do experiments. To be assured that we do the right thing, we do a useful thing. This one is the first expression, the first basic thought on machine learning. The second one is the continuous world. What does this mean? I like to, since my handwriting goes worse and worse during the lecture, I like to write it in the real world. Objects near each other, that is the neighboring objects, share similar properties. This is the meaning of this clause, the continuity world. This is as the assumption. We assume that the world we live in is a continuous world. That is, there is no jump from one point to another point, just a smooth movement in small neighborhoods determines properties of the objects. In a real world, objects near each other, the neighbors, the neighboring objects, share similar properties. This is the continuity assumption, the continuous world. That is, people living in Africa share a same or similar skin color. People living in some city speak with similar accents. How this assumption helps us? How this assumption helps us? How this assumption helps us? It helps us by given train data x1, sorry, this must be superscript, let's write it again in text, how this assumption helps us. It helps by extending properties of known and previously identified objects to the unknown and unseen objects. This is the help of this assumption. This assumption helps us to extend properties of the known objects, that is the given training data, to unknown objects, the unseen, unknown, new, unlabeled objects. We know that to infer properties of unseen object, it must be close enough to some known object. These two assumptions, the notion of latent and observable world and the continuous world, helps us to set up the science, the discipline of machine learning as a main and very useful part of artificial intelligence. Here I will stop for your questions. If you have any questions, please raise hand and ask your questions. Then we will go into some details of the learning tasks. Okay, seems that there is no question. Suppose that we are given a set of points like this one. We say this training set, this small blue circles, a training set. Each point could be expressed by xi and its corresponding yi. We write index of the instances as superscripts. xi means the ith instance. Please do not confuse it with xi, which means the ith feature. So we are given a set of instances, a sample. We say this is sample. A sample is a set of instances. Each instance is defined by its features. xi may be a vector, maybe a scalar, but we say here xi, we treat both the scalar and the vector one the same. Yi is the label, and we are asked to predict the yi. Here's x. This one is subscript denoting the feature ID. Here's some questions. For x1 being 1.1, what will be its corresponding y? Note that we don't know the actual process generating this sample. We don't know who generated this sample. Remember the box and the numbers coming from it. We don't know. But from our knowledge from statistics and math, we could assume that, assuming is a key phrase here, we could assume that these points are coming from a straight line like this. The straight line is defined as y equals w multiplied by x1. Yes, Allah says that linear regression used to find best fit line. Yeah, here a linear regression is fine to fit to the data, but how did we come up with a linear regression? Why did we use linear one? It's just an assumption. It's just an assumption that these points all are coming from a straight line, and the line predicts that y must be 1.5. Our learning task comprises of 2 steps. Here, our learning task comprises of 2 main steps. What is these steps? The first step, 2, is to assume that a line of the form y is w multiplied by x is generated the sample. This is the first step. The second step is to find the line. We know that it is a line. Which line we should find? We should find the line. For training data, we know y and x. We should try to train finding the line, that is y equals w by x, and these are known values. W is unknown value that is called parameter. W is an unknown parameter. We should find yeah, you're right, we should find the W the process is finding the W is called the learning process. Which needs a learning algorithm. To summarize, this is the learning algorithm, LA, not Los Angeles, it's learning algorithm. What this algorithm takes as input, it takes 2 pieces of information. The first one is the training sample, and the model type. Here, assuming that the line is the generator of the points, our model is line. And what does it produce? The learning algorithm produces a trained model, that is a model with tuned parameters. W is the single parameter, since we assume that y equals w by x1. W is the single parameter. It may take several values from negative infinity to positive infinity, and we must try to find the best 1. How we could find the best W? There are many ways to find the W. Here I write just a simple case, a simple one that generates a closed form solution, and we go on the lecture with other material. Suppose that we have x1 and its corresponding y1, x2, y2, dot 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 dot, x sub n, the nth sample, and yn. To be more general, suppose that these are vectors with several features. In the figure we see just, x's are features, y's are labels. Suppose that these are features, each instance is a vector of features, and this is a scalar value. We have n instances with m features, that is, x of 1 is a vector like this, a vector like this. The training data could be generated by sample. We don't know, just we are given the sample and we are asked to predict the y's for unknown instances. I can write these values in matrix form like x n by m and y, matrix y, or a column vector y, n by 1, and the w the vector of w like a column vector of w, w1, w2, 2, wm transposed. I can write a matrix equation like this: x w equals y, x w equals y, or following our earlier notation, wtx. There's no difference. N is the n is the number of instances. M is the number of features. N is the number of instances. Hello? You hear me, hello? N is the number of instances. Both of these matrix expressions are the same. Both are the same. We can write this, both of these equations. I will select this one, the text uses this one. I will select this one and go on with justifications. If X is a square matrix, then it would have a, if X is a square matrix, then it will have a inverse matrix. Then I could multiply by its inverse. But in general, since in general n won't equal to m, X would be a rectangular matrix that has not inverse. We could make some justifications to build up an invertible matrix here. XT means X transpose X. W equals X T Y. I multiplied by both sides by transpose of X. Now this is a square matrix. It could be invertible if your samples are where samples are independent of each other. This could be invertible. Then I invert this one and multiply by both sides by the inverse of this one. XTX inverted multiplied by the left side XTXW. The right sign is also multiplied by the inverse of this induced function, induced a square matrix. XT Y. This whole expression is equal to the identity matrix. It equals to identity matrix, the matrix with all zeros except the diagonal elements, and we have here IW equals the same thing. Let's write the expression once again. IW equals XTX minus 1 XT1. We could not drop I because it's identity matrix, and when identity matrix is multiplied by any matrix or vector, it does not anything, no scaling, no shifting, and we could simply drop this term here, having the best value for W. This is called the closed form solution. Any questions? Any questions on this? This is called the closed form solution, an algebraic way of finding the best W. Once again, coming to the original problem, we had some sample. We assume, please note to this word assume. We assume that this is a line that generated the sample. Any other assumption may lead to, or definitely lead to, another model with another type and number of parameters. Another will require another procedure for finding the best way, the best set of parameters, the best model. This assumption is a simple one, but very tough in some scenarios. For instance, suppose that we are given a set of points and we are asked to find, we are given a set of points and we are asked to build a model that resembles that emulates the unknown hidden process generating these samples. Someone may assume that it is a line. As you see, someone assumed that it is a line that actually generated these samples. He did the closed form solution, find the W, and come up with this line with so much errors. The line, the perfect line, is close to the points, but this line is far from many of the instances. Another assumption may be a quadratic form. This is something like Wx. Another assumption is y equals W1 x1 squared plus W2 x1 plus W3 as a bias term. We will talk about it later. This one fits perfectly to the instances, to the sample. We know actually that these points are sampled from a quadratic function, a degree 2 polynomial. This one is something like degree 9 polynomial, that is sigma of I from 0 to 9 Wi x1 to the power of I. A polynomial of degree 9. Here you see several big differences in the three models. The first model has large training errors, that is, it was not powerful enough to capture the actual relationship between the instance features and its label. So it is too simplistic, too simple. This one also fits the data perfectly, but it is too complex. This one is best one, enough complexity, not simple, not complex, but enough complexity. We call models like this that have large training errors models that underfit the data. They are too simple to capture the interrelations in the data. Here, the underfitting model, a model that is too simplistic. The relationship between the features and labels are more complex than the model parameters. This one with enough complexity has enough number of parameters, enough capacity or complexity to capture the relationship inherent in the data, and this one overfits the data. It has non-required complexity that may mislead the learning algorithm, mislead the learning procedure. Okay, we close this lecture here at this point, and I'm waiting for your possible questions. We will continue this topic in the next session, which we will held in Monday, I think. If you have any questions, here we could have a discussion, a short discussion on this topic. To conclude, we defined what is learning, machine learning. What does machine learning do? The two assumptions, the latent and observable worlds and the continuous world, help us to build learning algorithms, and we started a simple example called linear regression to demonstrate the mentioned topics. Any question? Okay, goodbye to the next lecture session.